Okay, welcome to Astronomy, AST1002, Section 1 at FloridaA&M University. I am streaming this lecture today because I am confined to my house due to the flu, and I've been told not to go out in public until I do not have fever symptoms for 24 hours. So, lest you miss any important information and we fall behind, I'm going to try to use the Google Hangouts streaming technology to provide you with a virtual lecture experience in lieu of not being able to have the physical lecture today. I will turn on the question and answer app at the end of the lecture. So please stand by at the end of the lecture to ask any questions you might have. So let's get started. Let me share the relevant part of the lecture on my screen. Let me make sure, okay, that's showing up. Bear with me for just a moment. Okay, welcome to Astronomy. Okay, welcome to. 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 Dateline, London, 1665. It began in London in the poor, overcrowded parish of St. Giles in the Field. Bubonic plague was known as the Black Death and had been known in England for centuries. It was a ghastly disease. The victim's skin turned black in patches. Excuse me, I'm getting some very strange feedback here. Let me the hell's going on here? Okay, well, I'm going to have to assume that you can hear me, and I'll just go to the next part of the lecture, because this is not going to work. This part here is not going to work. So I'll go to the next part. So let's just get into the regular lecture. I had some preface comments that I was going to make. Trying to get my screen share to share the next part of the lecture. Okay, here we go. Okay. Okay, so last time when we ended with the development in the knowledge of the universe as being described by the heliocentric view of Copernicus, as opposed to the geocentric view that was the reigning wisdom for years, and of which Claudius Ptolemy was the main proponent of. So what we're doing now is we're moving into the period in which now mechanics is being developed. And so now in the history of astronomy, science, history of physics, we're seeing now the development of mathematical descriptions of motion, which provide some understanding of the causative forces that cause motions to change, and the conditions under which motion occurs at all or doesn't occur. Motion at constant speeds, motion changes in the state of motion of objects, and acceleration of objects, which is changes in the speed and direction of motion. Okay, next slide. Okay. Okay, so why do planets move the way that they do? Gravity basically is the answer to that question. Gravity is a specific force. It's one of the 4 fundamental forces of nature. It is by far the weakest force, but also the most important force in the universe, as it is responsible for the large-scale structure of the universe, the distribution of matter, what we observe as the distribution of matter in the universe. And by itself, however, the observations of the distribution of matter in the universe actually can't be completely explained just from gravity alone, and we'll talk about that later. So Galileo is not considered the inventor of the telescope. The invention that we probably will never know who invented the telescope. The technology of optics, which gave rise to the telescope, kind of emerged simultaneously in places around the world and then converged on Italy during the Renaissance, primarily as a technology, a military technology. Galileo Galilei could be considered the first defense contractor, as he was actually hired by the Italian Navy to use telescopes to develop, to show how telescopes could be used in order to spot enemy ships approaching harbor before the ships knew that they had been spotted. And then also he was also employed to analyze the trajectories of cannonballs as well. However, he is considered the first user of a telescope to use a telescope for detailed astronomical observations. And he made significant discoveries. He discovered the Jupiter's moons. He also recorded the phases of Venus, which was a very important observation to support the heliocentric view of astronomy, at least in the structure of the solar system. The phases of Venus, the phases that are observed and the phases that are not observed, and the relative size of Venus as it's observed going through its phases, is absolutely consistent with Venus orbiting the sun as opposed to Venus orbiting the Earth. Galileo also experimented with falling and moving objects. As I said, part of this analysis was analyzing the trajectory of cannonballs. And Galileo actually was responsible for recording the first theory of relativity, the Galilean relativity, which provided for understanding the effects of relative motion between objects. And also it was Galileo that first provided a mechanism to understand the acceleration due to gravity of the Earth. So Isaac Newton discovered the laws that apply to all objects. These are the laws of motion, the laws of mechanics. The empirical rules that simply describe the phenomena is pretty much, Galileo is considered responsible for those. However, whatever is observed has to be consistent with the theoretical description. So for Newtonian mechanics to have been considered a correct theory, he had to show that his mechanics could predict what was actually observed with respect to motion of objects, and particularly the motion of the planets. So Newton's first law of motion is really a Galilean result. The first law of motion is the law of inertia. Objects in motion tend to stay in motion. Objects at rest tend to stay at rest. As long as that object is not acted on by an external force, then the state of motion of the object will not change. Now, Newton's second law, which we typically write as force equals mass times acceleration, but it's really more correctly written, I think, as, even though it's mathematically equivalent, more correctly written as A equals F over M. This feedback is really bothering me. I think I know what's going on here. Bear with me just a moment here. Okay, I think I've solved the problem there. Sorry about that. Okay, so Newton's get back to my. So Newton's second law, F equals ma, or acceleration equals force over mass. It's a better. The way of writing it that way is better empirically, because we don't directly observe forces. We directly observe changes in the state of motion of objects, and then from that we deduce what forces are at work. So simple examples of this, right? If you speed up a car, there is a if you apply additional force from the torque of the engine by hitting the gas, the car speeds up. Also, you will notice that if you have a cup of liquid in the car, the surface of the liquid will, the orientation of the surface of the liquid will actually point towards the direction of acceleration. Well, that's kind of interesting. We'll talk about that. That's a reaction. And we'll talk about action-reaction forces. So the velocity is the speed and direction of an object's motion. So if a car is moving at 60 miles per hour, the speed of that car is 60 miles per hour. The velocity, however, includes not only the speed of 60 miles per hour, but also the direction. So the velocity would be described in this case, as shown in the slide, as 60 miles per hour east, if that is indeed the direction the car is moving in. Now, to be clear, the direction can be described in any way, right? I mean, the car could be going southeast. It could be going, you know, a certain amount east and a certain amount south, or a certain amount east or a certain amount north. The directions are not limited to the north, south, east, and west, right? You can move in any direction, any combination of those, right? Okay, sorry, moving a little too fast here. Okay, so a change in velocity is called acceleration. So this is very important. Acceleration is not just a change in speed. It's also a change in the speed and the direction. Now, certainly you can have cases of motion where the speed is increasing only and the direction is not. Certainly you still have acceleration in that case. However, because acceleration also takes into account direction, then an object that's moving at a constant speed but whose direction of motion is changing is also undergoing an acceleration. And again, as the picture shows, the surface of the cup of coffee or hot chocolate or whatever that is, or beer, I guess it would be a stout, it's kind of dark Guinness perhaps, would point towards the surface, would point towards the direction in which the force is directed, or the direction of the acceleration. So that means that in this particular picture, we are to take from this slide that the direction of the acceleration for an object executing circular motion points towards the center of the circle which defines the motion. This is called centripetal acceleration, CENTRIPETAL, the so-called center-seeking acceleration. Excuse me. And unbalanced forces, as we've mentioned before, causes acceleration. So if there's a net force in an object, the object speed will change at a rate given by the force divided by the mass of the object. Mass itself, which is a property of matter. All matter has mass, and all mass has inertia. And oftentimes the response to an object of whatever given mass, how that object responds to a given force is, in a sense, the measure of the inertia of an object. Objects with larger mass tend to have more inertia, so it's harder to change the state of their motion than objects that have less mass. Greater forces mean greater acceleration. So in the picture below, the young lady is pushing the object on the cart. She pushes at a particular force, and the acceleration of that object is given by the force applied divided by the mass of the object. If the mass of the object increases, then the same force will result, as previous, will result in a smaller acceleration. Okay, so now let's discuss a little bit Newton's third law the third law is a source of, sometimes a source of confusion in analyzing motion. So Newton's third law, forces occur in action-reaction pairs. You've probably heard Newton's third law as stated as, for every action, there's an equal and opposite reaction. So forces always occur in action-reaction pairs. However, the two forces of the pair are equal in magnitude and opposite in direction. So in the example given in this slide, the astronaut basically throws a wrench in one direction. The force that's required to accelerate the wrench from being motionless to moving at a particular velocity is directly opposed by the force that the wrench applies in reaction to the astronaut. So what would end up happening is that the astronaut would move in the opposite direction as the wrench. The wrench is a smaller mass than the astronaut, so the wrench is imparted a much larger velocity than the astronaut is, being having a much larger mass than the wrench. So on the Earth, I'm sorry about the problems with the encoding of the accelerations. I will try to correct this here. I'll just speak what it should be. So all objects on Earth fall with the same acceleration. That is the acceleration due to gravity. That is an acceleration equal to 9.8 meters per second squared. This has been confirmed by experiment. And experiments on the moon have also shown the same phenomena, but with a different value of the acceleration due to the moon's different mass. So this is one of the laws of nature, or the laws of motion, that we expect to act the same way everywhere in the universe. We don't expect that there would be places in the universe where the laws of motion don't act. And I will share the actual test of the moon, which the Apollo astronauts conducted in 1970s. So let me give me a moment to pull that video up. Okay, and should be, this was actually Apollo 15 is where this was done, that was the mission that was perform this experiment. Okay, let me skip the ad here. You got to watch commercials on YouTube now, unfortunately, and I'm forced to watch the ad. So I'm not forced to watch the ad. I'm gonna skip the ad, and then I'm gonna stop the video. I'm going to go back to the beginning, and I'm going to share the video. I think I can bring it into the streaming hangout here. Copy. Okay, so I want to, let's see. Okay, more. I need to more apps. Add apps. So I believe. to the okay. So we will select okay. Okay, accept. Okay. Okay. So let me add this video to the playlist. Okay, add videos to playlist, and let me put the okay, search. So what the astronaut is holding is, okay, I need to push to talk. I hope you can hear me. Oh, your mic is muted, dear. Okay. Okay. So what he's tossing there, dropping is a hammer and a telescope and a. So basically, he's got a falcon feather and a hammer. Okay, so at least the laws of motion work out to the moon. We would expect they would work everywhere. Else in the universe. Me? Okay, I want to share my screen, people. I want to share the lecture. Okay. Wait a second to make sure that everybody's seeing the slides. You go away from the movie and back to the slides. Make sure everybody sees that. Hello. Oh, present to everyone. Yes. Okay. How do I small player? Okay, and how do I back? How do I get back to the? Okay, there we go. Okay, so all objects in Earth follow the same acceleration, also the moon, but it's different because the mass of the moon is different from the Earth, as shown by experiment. Experiments on the moon have shown the same phenomenon, but with different value of the acceleration due to the moon's different mass. The formula here should be written F sub weight. The force of the weight of an object is equal to its mass, m, times the acceleration due to gravity, g, of the planetary object that the mass is being attracted to. So this should be F weight equals mg. So for the Earth, g is equal to 9.8 meters per second squared. And for the moon, I believe g is equal to 1/6 of that value. So 9.8 divided by 6, I believe, is the whatever that is. So one thing about gravity is it's always attractive. We have not observed repulsive gravity, at least not repulsive gravitational repulsion between objects due to their mass. The greater the mass, the greater the attraction. And the description of gravitational force is proportional to the product of the two masses that are attracted to each other. Note, however, that regardless of how the masses compare to each other in magnitude, the force of attraction of one to the other is equal to the force of attraction of the other to the one. So again, equal and opposite forces. This is why the two arrows drawn here are drawn at the same length. The force is the same. Now, the resulting acceleration will be different, right? Because the second mass is larger than the first mass. So for the given force of attraction, the acceleration experienced will be smaller for M2 than for M1. So the greater the distance between the objects, the weaker the attraction, the smaller the force. The gravitational force varies as the inverse square of the distance between the two objects. So that means that the force magnitude, gravitational force magnitude between two gravitationally attracting bodies is basically given by 1 over the distance between the two bodies, between the centers of the two bodies. Okay. Let me take this for a moment, and I'll be right back. Okay, I'm back. Let me mute again. I was getting a call, and I need to take this call. So please bear with me. I'm going to mute my microphone. I'll be back in a moment. Okay. All right, I'm back. Okay. So the greater the distance between the objects, the weaker the attraction, the smaller the force. And the force goes in inverse square law of distance, as we said. So putting this all together, and again, I apologize for the equations not coming out right here. But let me just tell you how this should read. Okay, you're going to have to bear with me a moment. I need to mute my microphone again. Okay, I'm back. Sorry for the interruption. Okay, so that formula on that slide should read F sub grav, the gravitational force, equals capital G times M1 times M2 divided by R squared. M1 and M2 are the two masses in attraction to each other. Capital G is a physical constant of the universe called the universal gravitational constant. And R is the distance. Okay. And again, I'm gonna. It's not activated, but I will activate the question answer at the end of the lecture, so you guys can ask questions. I'll have to go back and enable that app in my control room or whatever, but you'll have a chance to ask questions. You can chat them. You can either chat them or you should be able to chat to me as well. I think, right? Okay. All right. Okay. So we talked about the type of motion that's important here because this is an astronomy class, is orbital motion. And so in the context of Newton, in the Newtonian context, the context of Newtonian mechanics, what is an orbit? How should an orbit, what's the correct way to describe an orbit? So if you consider the following situation. You have a cannon and you're firing a cannonball at higher and higher speeds. At some point, if you fire the cannonball at a high enough speed, the acceleration of the cannonball towards the Earth, the change in the direction of the acceleration of the cannonball towards the Earth will exactly match the direction of the change in the direction of motion. That is to say that they won't be the same, they'll just change at the same rate. So once that occurs, then you have a situation where you've launched something into orbit. It's in a stable orbit. And so because of that, an orbit can mechanically be described as the state of motion where an object is in perpetual free fall around an object. It's falling, but it never reaches the surface of the object because it was fired at a speed sufficient such that its change in its direction of acceleration compared to the rate of change of the direction of motion is such that the direction of motion never points back toward the object. And if you actually fired the cannonball at yet a larger speed, it would escape the gravitational influence of the Earth altogether, and it will be launched into space. Okay. So now this centripetal force, which I mentioned before, the center-seeking force, that force comes from the gravitational attraction of, say, a satellite to the Earth in its orbit around the Earth. So an analogy of this is, swinging an object around your hand, an object tethered to a wire, and you swing this object in a circular path around your hand. The force, the tension that develops in the wire, which is really a reaction to the force of the wire wanting to make the object stay in the orbit, remain as sort of the remain under the influence of the center-seeking acceleration. The force that points towards the center of the circular path of motion is the same as gravity. It's an analogy. It's analogous to gravity. Okay, so I'm gonna have to stop again, and I will be back in just. Okay, I'm back. Hopefully that will be the last interruption for the remainder of the lecture. Okay, so let's go to the next slide. So the astronauts in the space shuttle, when the space shuttle was operating, space shuttle no longer operates. Astronauts float freely because they are in a room, essentially a container, the spacecraft, that is experiencing the same acceleration. Both the spacecraft and everything inside of it is orbiting the Earth. They're all in the same state of perpetual free fall around the Earth. And so if you're in a state, if everything around you is in the same state of acceleration, then there's no sort of relative acceleration between you and the object, and you can't really detect that there are forces at work. And this is why oftentimes and incorrectly, the state of floating in space is called a zero gravity state. It's not zero gravity at all. You just said that the force of gravity varies as the 1 over the distance squared. It's certainly less than the gravitational acceleration due at near the surface of the Earth at 9.8 meters per second squared. As you get farther from the Earth, the gravitational acceleration due to gravitational attraction of the Earth gets smaller, as it would have to, as described by the so-called universal law of gravity, with the 1 over r squared term. But in the case of the astronauts in the space shuttle and all the other objects in the space shuttle, they are all in orbit around the Earth in the same state of perpetual free fall. And so they float. You can actually do this same experiment at the amusement park. If you ride I forget what the rides are called now, but if you ride the ride that gives you a few seconds of free fall, you can take like a balled up piece of paper or something soft, like a Nerf ball or something. And when the carriage is released and you're in free fall, if you place the crumpled up piece of paper or the Nerf ball in front of you, it will just float in front of you because it is in the same state of free fall as you are, as the carriage is. So everything appears to float. Okay. As we discussed earlier, Kepler, the first law of Kepler was that the shape of orbits are elliptical. Circular orbits, of course, are possible, but a circle is just a special case of an ellipse. A circle is just an ellipse with zero eccentricity, and where the foci the focal points occupy the same location. So when you toss an object up, like when when a quarterback throws a football on the field, that football is executing it's executing a orbit, right? The type of orbit it executes, however, is an orbit that brings it back in contact with the ground because it's not launched with sufficient velocity such that the acceleration due to gravity forces it into a orbit around the Earth. Okay, so there are bound and unbound orbits. Elliptical orbits are bound orbits. They basically return to they visit all points of the path again and again and again. However, if an object attains high enough speed or is launched with high enough speed, it can basically break the gravitational attraction of the planet and be launched into space, never to return. These are unbound orbits. So the shape of unbound orbits are parabolas and hyperbolas, and bound orbits are basically ellipses. Okay, so Newton derived Kepler's rules from his law of gravity, and in fact, that was why Newtonian mechanics was considered a correct theory, because it recapitulated the observations of Kepler. So basically, the laws were tested by Kepler's observations, and their exact agreement showed that Newton's law of gravitation was correct. Later, later on in the 20th century, we learn that however Newton's laws are correct, they're not the whole story on gravity. Okay, so in review, let's consider the following questions. And what I want to do here is I want to do a poll so you can actually take a poll of these questions. Let's see here. Question answer. This feature is disabled. Oh, how do I enable it? Okay, let me go. Let me go to my control panel here, control room. Okay. Okay, oh, it's only the audio and the video control. Okay, let me add the question and answer. Okay, just bear with me, please. Bear with me for a moment. Let me go to okay. All right, looks like I'm going to have to go back into my account to get that to work. So let me go to my Google Plus account. Oh, whoops. I'm not, sorry about that. I have to use the wrong window there. All right, so let's go to my dashboard. Oh, that's not what I want. I want the Google Plus. I want to go to Google Plus. Oh, I've already signed in. This is silly. All right, let me try this. Let me go back to the chat. Okay. So, you can answer the question in the chat if you like. And just give your answer in the chat window. Are people aren't allowed to? Okay. Okay, so let me go to Google Plus. Okay. So let me go to my and well, all right. Well, I'll get this working next time if we have to do this again. But in any case, let's just go through the questions. So the space shuttle is in a circular orbit at a constant speed of 28,000 kilometers per hour. How do we know a gravitational force is or isn't acting on the spacecraft? Is it A, the spacecraft is not accelerating since the speed is constant, no force equals no gravity? B, the direction of the motion is constantly changing. This counts as an acceleration. Forces produce gravity. Or C, the astronauts inside are weightless. No weight equals no gravity. So what's the correct answer here? The space shuttle is in a circular orbit at a constant speed. Okay, so we know from a circular orbit, the path is circular, which means that the direction of motion is constantly changing. In fact, the arrow that describes the direction of motion at any moment is actually rotating if you consider how the direction of motion changes over the entire orbit. So clearly, however the speed may be constant, the velocity is not because the direction is changing. So therefore, B is the correct answer. The direction of motion is constantly changing. This counts as an acceleration. Forces produce gravity. Okay. Your weight equals the force between you and Earth. Suppose you weigh 60 kilograms. Then the force on Earth is A, 60 kilograms, B, much smaller than 60 kilograms because your mass is much less than the Earth's, C, exactly 0, since only massive objects have gravity. So let's take this, analyze this according to what we've already discussed. The statement is your weight equals the force between you and Earth. Okay. Again, we know that the force between you and Earth is is equal and opposite to the force on the Earth between the Earth and you, right? It just points in the opposite direction. And we know that as described by the third law of motion, the action-reaction principle, for every action, there's an equal and opposite reaction. Then the force on the Earth must be equal to the force on you due to the Earth. So the correct answer to this question is A, 60 kilograms. Earth and Moon have a gravitational force between them. The mass of the Moon is 1.2% that of the Earth. Which statement is incorrect? A, the force on the Moon is much larger than that on the Earth. B, the forces are of equal size even though the masses are different. C, the Moon has a larger acceleration than Earth. So now let's take each one of these according to what we understand about the laws of motion. Let's start with C and go up. So C, the Moon has a larger acceleration than Earth. Well, that would be correct because the equal and opposite forces of attraction between the Moon and the Earth and the Moon require that the Moon have a larger acceleration because it has a smaller mass for the given force. So that's correct. That's a true statement. Statement B, the forces are equal size even though the masses are different. Well, that's basically restating C. That is correct, B. So it looks like the answer to this question is A, the force on the Moon is much larger than that on the Earth. Again, the forces are equal and opposite. Forces and accelerations are two different things, okay? Don't confuse force with acceleration. All right, so let's take a look at the Astro Tour. I think I'm going to have to let's see here. Actually, let's look at the different. Let's actually look at elliptical orbits. So now I'm going to click to. I encourage you, however, I've posted all of these tours in the Blackboard course documents section under tutorial materials. So please make sure that you take advantage of them and study them and use them to improve your understanding of these concepts. So let's take a look at the elliptical orbits tour. Okay, and I'm going to have to change what I'm sharing so you can see it. So let me go back to the Google Hangouts window and let me change what I am sharing. Hello? Okay. Let me change what I'm sharing. So I go to screen share. Okay, just waiting for the screen share to open up my desktop so I can choose what it is I want to share with you. Okay. Okay, so can you hear me? Yeah, you can hear me. Okay. Okay, just waiting for that to load in so you can see it. Okay, there it is. Hello? It was there and then it wasn't there. There it is. Okay. Okay, so let me go ahead. I'm going to see, I'm wondering if I need to add a Chrome app so that the whatever is viewed in the Chrome browser can be viewed. Well, okay, I'll just try this. We'll get it right eventually. Okay. Is that it? No, perhaps that was all. Okay. Oh, yeah, that's it. You have completed this exercise. Okay. All right. That's it for that one. All right. We're at the end. So let's take attendance. So let me open up if you go to the Blackboard, if you please go to the Blackboard and look in the announcements and look at the link for the attendance. I have to turn on the attendance so you can get access, so you can actually record your attendance. Give me a moment to do that. And then you can fill it out. Let me close that. Let me go back to this. Let me go back to this. Okay, let's, okay, the attendance form is now accepting response. Please go to the attendance form. The link is given in Blackboard, and the Blackboard for the course, and also was on the announcement that went out by email. Please go to the link, the URL, and register your attendance. Make sure you know the last 4 digits of your FAMU student ID. If you don't know it, find out quick, because that's how I'm going to keep track of folks and assign grades. So I don't want you to get lost in there. So please go. The phrase for today is elliptical orbits. The phrase for today is elliptical orbits. Let me go ahead and share that screen so you can see what I'm talking about. Okay. Now that's what you should see when you go to the attendance site. Okay, the attendance will be on for a few more minutes. And the number or phrase displayed in lecture will say it's elliptical orbits. Elliptical orbits. Okay, I see there are 8 viewers here. So I don't see anybody. Oh, okay, 3 responses on the attendance. I see 8 viewers. There should be 8 attendance responses, unless only 3 of the 8 people are actually taking the course. Okay, so this is weird. How can I have 9 responses and only 8 people in the lecture? So I'm going to stop accepting responses because I don't want any cheating on attendance. There are 8 viewers, so there should be 8 responses to the attendance. Only 8 people are in class, virtual class. Okay. All right, so that's it for chapter 3. If I am medically cleared to leave my home, then you will see me on Thursday. Otherwise, we'll do this again, and I'll add some more features. You'll be able to interact and ask questions. Let me ask, actually, does anybody have any questions? And I would think you'd be able to chat them, basically. Let's see. Okay. Okay. Well, it doesn't look like I'm able to receive chat messages from the viewers. I'll have to figure out how to do that so I can answer questions. All right. Well, anyway, have a good day. See you next time.